Okay, so now we're going to look at this equational proof framework and see how to apply this framework to prove theorems, either absolute theorems or relative theorems. So you can imagine that the most obvious type of well-formed formula or theorem we would want to prove using this equational style proof is some kind of equivalence. And so template 1 shows us how an equational style proof looks in order to prove the equivalence of A and B. So here we simply start with one side of the equivalence, establish a series of equivalences until we get to B, and then this is a valid equational proof of A equivalent to B. And the reason that it's valid is because it follows directly from this meta-theorem here that we introduced in the last video, right? So here is where we establish, so in our equational style proof, we establish all of these equivalences, and then the meta-theorem tells us that, in our case, A will be equivalent to B, because we start with A and we get B at the last step of our equational style proof. Right, so we establish all of these equivalents where we start with E and we start with A and we end up with B, so this meta-theorem tells us that this is a valid proof of A equivalent to B. We can do this in a different way by applying this corollary here instead, which is maybe not what you would think to do, but in some cases it's actually more convenient to do this. So in this case, we have no assumptions here. So we want to establish this as an absolute theorem. So in that case, the only things we can use are axioms or absolute theorems because they don't require any hypotheses. So if we start with something like that, we know that the empty set proves any of these types of theorems. Then if we establish an equivalence with what we're trying to prove, A equivalent to B, then that corollary says, so if we can prove what we start with, then we have a proof of what we ended up with. In this case, an plus 1 will be A equivalent to B, and A1 will be whatever axiom or absolute theorem we started with. And because we have an if and only if statement in that corollary, it doesn't matter in which case we start, right? Oftentimes it's easier to start with something we know and then establish its equivalent to something else, right? You follow your nose through until you see something that you know. Okay, so that's a very specific example of how to prove an equivalence between two well-formed formula. We can also, as I mentioned in the previous video, prove well-formed formula which may or may not be equivalences, right? So if we simply want to prove a well-formed formula A, we can also use the equational style proof by applying that last corollary on the previous slide. So here again, we have no assumptions, so our gamma is the empty set, and that means gamma, the empty set, only proves axioms or absolute theorems, so we need to start with something we know is true, establish some equivalences until we arrive at the well-formed formula we're trying to prove, or vice versa, start with the well-formed formula we're trying to prove and show that it's equivalent to an axiom or a proven theorem. Finally, if we do have some non-empty assumptions, so some gamma, this simply means that we can use anything that gamma proves, right? So we could use an axiom or a hypothesis, something in gamma, or a proven theorem, right? Gamma will prove any of those things. We establish the hypothesis, for example, is equivalent to something else, and we establish a series of equivalences until we arrive at A, and this is a valid equational style proof that gamma proves A. So we can do that, or we can start with A and get that it's equivalent to an axiom or hypothesis or proven theorem. So the only difference here is that we can use the hypotheses that we have, assuming that gamma is non-empty. All right, so that concludes an explanation of what an equational style proof is and sort of what it looks like. In the class, we'll look at a variety of different examples of equational style proofs so that you can get comfortable writing both Hilbert style proofs and equational style proofs.